Okay. So today we're going to do more isometry work. Try to figure out a little more about how these isometries look in the plane. These figures are, I guess, like non-standard tessellations of the plane with the pentagon, not a non-regular pentagon. But okay, mathematicians study things like this, and they also study things like this on the disk or the hyperbolic plane. And a lot of the groups that we consider are really groups of symmetries of these types of figures and diagrams, things like that. Some of them are, so the ones for these are discrete groups, meaning that every time you perform an isometry, it's sort of a very rigid motion that actually moves things really far, and then some are continuous groups. That's usually rotating or continuously translating. So we'll see some of the classifications, not of these, but of things like them. That's what we okay. So last time we ended with a theorem that talked about isometries, but we didn't really prove it. So we're going to prove it today. And let me just recall what the theorem said. It said the following are equivalent for a map B sending Rn to Rn. A is an isometry, meaning it preserves distances and it fixes the origin. The origin is the origin. B preserves dot products. B dot W. B of V, W. All W. C, B is an orthogonal linear operator. Okay. So through this, I want to kind of make a cycle, prove that A implies B, B implies C. The hard part here is B implies C. Harder part. So let's look at A implies B. A little trivial, but okay. Well, okay. This is true. So why is this true? Is an isometry. What is recall what that means? Isometry. Is that if I take the length of V of U, that's okay. So that's for this case. When 0 goes to 0, in general, you don't have to have that. In general, you just have that this is true for the difference of two. This, I'm taking, okay. The definition of isometry really is that the distance between two vectors, which is this, unchanged. However, if I take B to be 0, and I know 0 goes to 0, then I get this. This is the definition of isometry, preserves distance. This is the case. how would we prove A implies B? Let's say we have an isometry that fixes 0. How do we show it preserves dot product?
Would it just be by the definition that dot product is the
Okay, but the dot, but it's not, right? It's not just the multiplication of the two vectors magnitudes. It's that times cosine of theta, where theta is an angle. So in the definition of isometry, we're saying it preserves lengths. But we didn't, it doesn't, the definition doesn't say it preserves angles. The point is that it will preserve angles, but preserve lengths. Yeah. And if U and V have length 0, and they're both 0. Vector of length 0, 0. So this is a trick that we sort of use to prove that formula that you're just mentioning, which is just say take U plus or minus V and square it. We know that we can just say phi of U just phi of V squared. This is equal to U minus V squared. But on the right-hand side, we get that this is U 1 of U squared minus 2 dot V plus 1 of V squared. On the left-hand side. On the right-hand side, we get, just again, using the properties of dot product, remembering that the magnitude squared is something dot itself. Yes. Now, since this is true, since we have this is true for any vector U, it's true for U and V and U minus V. So we can cancel out this, and we can divide by 2, negative 2, and we get U dot V. So maybe that's just a trick. Just remembering norm squared, our magnitude squared is something dot itself. That gives us B implies, or A implies B, and now we want to look at B implies C. And as I said, so there's a kind of, let's say it's a fairly elaborate proof for this, in art, but let me give a slightly different proof. And for my proof, I want to make a comment. First comment: if P1 Vn is an orthogonal basis, then there is a linear isometry into Rn such that T of Bi equals EI. EI being the standard. It's 1 on the I row and 0 everywhere else. Why, okay, so why is this true? Someone can tell me why this comment is true. Maybe I'll ask the inverse question. Why is it the case that I could go, why could I have something sending EI to VI? So on the homework last week, there was a problem that asked you guys to write down a matrix for certain rotations in three-dimensional space. But how did you guys do it? Monday mornings. In history. You drew it in the coordinates 3 space, I think. Yeah, okay. But then how did you write down a matrix? Okay. I agree with that. I agree with drawing it. But then once you got like the coordinates for what for what you wanted, what did you do with them? Well, how did you know? Okay. So in review, I know what I said, and I'm just wondering if people like got what I was saying. So if I have a linear transformation, right, and I want to write it in terms of the standard basis vector, like everything is written in terms of standard basis useful matrix. If I want to know how to write that matrix, and I know geometrically what's happening, I just ask where the standard basis vectors go. Like where does E1 go? Where does E2 go? Where does E3 go? I get that list of vectors and then I put them as columns in matrix. That's how I can write down a matrix representing a linear transformation. So of a rotation, I ask, well, where is this rotation sending my first standard basis vector? That's my first column. Where's it sending my second one? That's my second column. That's an easy way in terms of standard basis. If you do it with respect to different basis, that's completely off. Standard basis, that's how you do it. So here I have n orthogonal basis vectors. And if I ask you the inverse problem, sending EI to VI, do I have a matrix doing that? Sure. I'm telling you what the matrix is. So if S, or well, let's call it A equals the matrix B1, B2, I just put these guys into columns to make an n by n matrix. Then A times EI equals VI. Right? Sorry, guys, maybe this is why you are confused. Maybe not. I should have said orthonormal. Right? So if I have this matrix, the multiplying by this matrix will send EI to VI. And if this is a V1 through Vn are orthonormal, that means this is an orthogonal matrix. That's something we've seen last week. So this is an orthogonal transformation. And if I want T sending VI to EI, I just take the inverse. Let T VI is equal the inverse. Well, T of any vector, really. B the inverse. But that'll do the trick. So is it clear? Questions? Ruling right in the middle of the semester. I thought Thanksgiving should be moved up a month. Yeah. You voting yes? Okay, you're right. Okay, guys, so this is a true comment. We can always do this. And so why do I make this comment? Well, I want to use it to show that B implies C. So remember what B is. We're going to assume that we have an isometry phi, and because of B, we know phi is going to preserve dot products. Now let's suppose phi of E1 or EI, sorry, is equal to BI. So I'm just writing down the name for where phi sends EI. And by B, remember we're assuming B, we want to include C, B1 through Bn are orthonormal vectors. Right? See that? Because E1 through En, they're pairwise orthogonal and they're unit vectors. And phi preserves by B, preserves the dot product. So that means that these will also have unit norm and they will also be orthogonal. Okay. But we know that if we have an orthonormal, if we have an orthogonal set of vectors and they're all non-zero, and these are all non-zero, those are unit vectors, that they're linearly independent. Something we showed. And so that means that this is a basis. It has n linearly independent vectors and an n-dimensional space as a basis. It's an orthonormal basis. Orthonormal basis. Okay. So a T from the common exists. This is a linear isometry. It's linear. Multiplication by a matrix. Let's consider. Sorry. I want to write star. Yep. So consider T composed with B. So this is an isometry. If you have two isometries and you compose them, that's an isometry. That's just from, you can prove that very directly from the definition. But it kind of makes sense. Distance, and you do something else that also preserves distance, finding them, in sequence. This is an isometry. It's an isometry. And decompose B of 0, B of 0, but this is 0 by A. Well, okay. This is 0. You can easily see this is 0 by part B too. So I'm not going to. I know I'm only assuming B, but if I take B of 0 and dot it with itself, it's 0. So B of 0 must be B of 0. Satisfies this property. It's an isometry that satisfies that it sends 0 to 0. So by what we proved that A implies B, it preserves dot product. Now let B equal actual concrete column vector A1 through AN equal to 1. Then consider AI. This is equal to V dot EI. Right? Everyone agree? Now T composed of phi is an isometry. So this equals this. What is this? Question. What is this? What is this vector? Yeah, you guys are both getting that at the same time. Phi of EI, what is that? Well, we assume that phi of EI is VI. In the comment, we said there is some T such that T of VI equals EI. So phi is going to send EI to VI, and then T will send it back to EI. So this is just EI. So we look at this composition, say equaling X1, well, I'll write it this way. E1, En. Then EI equals AI. Am I right? The way I find BI, if I want this vector, the way I can find BI is I can dot this vector with EI. We just saw that if we dot this vector with EI, we get AI. But that means that this is equal to V. This is identity. Identity transformation. But T is an invertible linear operator. It's multiplication by an invertible matrix. We can multiply both sides by its inverse. And then the inverse, which is a linear transformation. Orthogonal linear. The whole point of B implies C is to show that it's linear. So this is a linear transformation. Okay. Question? Yeah.
I didn't have a question. I was just
Okay. Oh, you were like honing in on the idea. Okay, I got it. All right. So that's B implies C. Of course, C implies A is immediate. C implies A follows from the fact that orthogonal linear operators preserve dot product, which means that they preserve norm or magnitude, which is length. This C implies A follows from what we've already done. Well, okay, maybe we can just say, we say if it's linear, V of U minus V of B equal to, because it's linear, this, because it's orthogonal. Of course, linear maps take the order. All right, so that was it from 6.2. We want to kind of move on to 6.3. But actually, that was not it. we had a couple more things that we wanted to say. So this says that if our isometry preserves the origin, we're really just looking at orthogonal transformation matrices, which are something we've already considered, and we'll consider a little more as we go. And so what then? Still on. That, I think it's must be okay. All right. So first let's give ourselves a little more notation. So we'll write, and this is Arden's notation, write MN for the group of isometries is a group. Certainly if we have an isometry, we can just take its inverse. We'll get off again my isometry of isometries. Of Rn. So then there's a corollary of this theorem, which says that if we have an element of this, then we can express it uniquely in the following way. And any p, let's say any f in n can be expressed as T of A P, where phi is a linear isometry. Let's just write ON, and T of A is a translation by A. A, which I'm just following Arden's notation. So in particular, if you look at, so I mean, the reason for this is the following. So the reason, look at T of negative f of 0. So translation, we'll all agree that is my isometry, right? If I pick up space and I translate it, I'm not changing distance. I'm moving all the vectors by the same. So if f is an isometry, then this composition is an isometry. I'm not writing the circle composition, it's just that's the group operation. But the one thing I can say about this particular isometry is that if I look at what happens to 0, this is minus f. So I'm translating f of 0 by negative f of 0, whatever it is, right? And so this is equal to 0. I translate something by its negative, I'm translating it back, adding negative f of 0 to f of 0. Maybe this is confusing. Let me just, what is T of A? T of A of a vector like x, this is just x translation. So, but if I have an isometry that sends 0 to 0, we know that it's one of these orthogonal guys. So that means that T of equals phi for something, and then we can compose on the left the T of F of A. Get that looks like this. Where A is F of. All right. So now there are some relations which come in handy. Relations. One is that if we translate on the left, we can all and multiply by phi, where phi is from this theorem. So phi sends 0 to 0. This is equal to phi of translating on the right, where A prime is equal to phi of A. And we can see that but just by going ahead and, I'm sorry, I phi inverse. I want to say the other way around. A is phi times A. Just let's check it to make sure that I got the right order. If I take phi of T, no, I think I had the right order. And okay, phi of TA x, this is equal to phi of x plus A. Equal, now we know phi is linear, so we get phi of x plus phi of A equals guys, I'm not able to read my own notes. Sorry. So I want to start with this side here. So I've got phi TA prime. So now that I've done that, this is T of A prime. That was right the second time. Yeah. All right. Okay. So the point really is that you can take a translation and move it to the other side if you, so long as you change what you're translating. Another point about this is that note translations. From a normal subgroup. If I take this equation, I multiply both sides by phi inverse, get this. Means you can actually quotient by it. If you do quotient by that group, you get something isomorphic to the orthogonal. All right. Now, one of the things that's useful to understand if you're going to ever apply this stuff, and something we've already talked a little bit about, is how do we have an orthogonal, if we have a transformation and we do a change of coordinates, how do we write it in the new coordinate system? So what I want to do is bring over a diagram, or maybe, yeah, maybe I'll just look at this. Well, I'll bring it over. We'll look at it. So the idea here is, and this is not just ortho. So here, this I've got two coordinate systems. It's not a transformation. It's not an isometry from one to the other in this case. Like I can see that I changed some angles. But the statement and the proof of change of coordinates is just generally true, regardless of whether this is orthogonal, an isometry or not. So the idea is I've got some coordinate system here. So you imagine yourself at a particular point, maybe just the origin, and you set up a grid for your space. Make yourself coordinates, right? And then there's some other point, maybe their origin is over here. And they have a different coordinate system set up in the same space. It's the same space, the space is the space, but the way we label points is different. So we have a transformation though, it's like a dictionary. Right? We both look at the same point. I say, I call that point 2, 3. You say, you call that point -5, 5. Okay. And this map is the way to transform my coordinates to yours. That's the idea. That transformation is algebraic. It's given by an equation. Matrix plus maybe a translation. But there's a formula to say, here's, if I'm given a point x1, x2, you can give me the expression for that point in your coordinate system. It is the same point though. That's what this map is doing. Translating languages about the same thing. These maps we're imagine doing something to our points. So this map is, I imagine, as like an isometry. So let's take both of our spaces and rotate them. So you take those points in those spaces and rotate them. We'll sit here and look at that rotation, but everything in the space rotates by a certain amount. And then I say, okay, well, I have a formula in my coordinates that says what happens to that point in my coordinates. It was 2, 3 in my coordinate systems. Now it's 5, 7. Okay. And you want to know what happens in your coordinate system. The point is all we need to know is that a dictionary, and we can tell you can tell me, or I can tell you, whatever. If one person knows what it is and we know the dictionary, we can translate what's happening in the other coordinate system. The way we do that, if we call this guy eta, which I am, is we just note that, well, if I change into your coordinate system, your notation, and we do the same thing as we're doing over here, and then we change back to my system, I will get the same kind of transformation. Because this is just a dictionary. This isn't, nothing's happening to the space. This is the same thing that's happening on both sides as far as the rotation or whatever. So the point is we can translate that into an equation. We can say, okay, well, translate into your coordinates into mine, do the same things that's happening in your world as in my world, and then translate back. And we'll get the way of seeing what happened in your world from what happened in my world. This is a very non-technical explanation of a change of coordinates formula. But the change of coordinates formula is really just this. And this is the equation. If I called it M here, and M prime. I do an example. But this is the equation we want to know. Because it's true if you're doing a change of basis in the vector space. It's true if you're dealing with isometries. It's true if you're changing it's true in a lot of different contexts. Now we're going to apply it to isometries, but this is just a true thing in a lot of contexts. This is an example. And here I'm going to let's say I have this coordinate system and let's say my coordinate system, I'm the one with the square usual grid, and my coordinate system has the origin here, which is your 1, 1 vector. So your origin is here. The origin for blue. But let's say it's the same grid. It's just you're translated over. We both have the same square grid. So your 0, 0 is my -1, negative. That's the way I write my point. So we can see what the transformation from mine to yours is, right? In other words, if I want to take my coordinates and write down, something in your coordinates, then I just take my vector and add 1 to each of them. Like this will send the origin to 1, 1 in your coordinates. We'll translate everything down. But we don't want to think of it as a translation. I don't actually want to think of that. I just want to think of it as rewriting the coordinates so that they're the same points, but now they're in your coordinates. Now, what we see is you take all of the points in our collective universe and you rotate them by pi/2 counterclockwise. So that means you're going to do this. You're just going to take, this point, rotate it here, that point there, this point will go here, so on. Rotate by pi/2 about you. About me, it's not rotating about me, rotating about you. So I want to know how I can write that as an equation in my coordinates. I use this formula. But first I need to know how things rotate about you. How do you write your formula? What's the blue formula for rotation? Counterclockwise. How do you do it? Last time we talked about symmetries of the plane. Rotation was one of them. You guys remember the matrix? Cosine theta, sine theta, negative sine theta. So if we use that matrix, this is equal to 0, 1, -1. Alternatively, you can ask in your coordinate system, where do the basis vectors go? Where does the basis vector 1, 0 in your coordinate system go? It goes to 0, 1. There's that column. Where does 0, 1 go? It goes to -1, 0. There's that column. So you know how to write it in your coordinate system, but I want a formula in my coordinate system. So all I do is I use this. For my coordinates, m of x1, x2. Well, okay, I'm kind of going, maybe I'll write this as, since I've got a matrix multiplication, I'm going to write this as x1, x2, like that, column vector. And so then make that into column vector equation. This is eta inverse of a eta, x1, x2. It's eta inverse of this guy. Now I can add 1 to both of these. x1 plus 1, x2 plus 1. I multiply this matrix. I'll get x2 plus 1, then minus x2, sorry. And x1. And then I have to subtract 1 from each. So I get negative x2 minus 2 and x1. Yeah, for me. Let's just check. So where do I go? Where do I go? Well, if I'm the origin, I go to negative, by my formula, I go to -2, 0. So I go here. My coordinates. That makes sense. That's this, and then I rotate it. Okay. So this is a very useful thing to be able to do. Very useful thing to be able to do. Okay. Any questions? I want to use that in a minute. Learn a little more about isometries. But this is general. It's not actually really about isometries. It's general. All right, so for 6.3, which we should just break into a little bit today, we have the isometries of the plane. We're going to study the isometries plane. And we give, so this is M2. And we have some generators of this group. In other words, everything can be written in the form in as a combination of the following three transformations. So I'll just say then M is generated. Generated means that what I just said by translations. Which write TA of x. This is just x plus a. Or if you want to put coordinates, this is x1, x2. Let's say a is the vector a1, a2. You have rotations, counterclockwise. Rho theta by the origin. The rho theta of x is just what we talked about last time. We take this matrix. Like this. And we have a reflection about E1 axis. But you can get all other reflections by composing this with rotation. About x-axis. Right, R x just equal to this matrix. There are a bunch of relations, which I'm not sure. I mean, one is this relation we talked about a second ago, but translate and then rotate. We can rotate and then translate by a different vector. But there are several others, and I'll just let you read about those in the book. But instead, I want to kind of state this theorem, and then next time, I think I'm going to just show about half of it, and then. It's actually not too bad. Okay. So this theorem says the following thing. It is a sort of surprising theorem, I think. 634. So it classifies isometries of the plane. So every isometry plane has one of the following forms. The one, or A, is when it's orientation preserving. So I didn't talk as much about this. In the plane, this is not hard because there is a natural orientation. Well, it's not a natural, it's an imposed one. But if you fix it, you can talk about whether something preserves it or not. So you can say, well, I'm in the plane and I know the difference between counterclockwise and clockwise. Now, yeah, I perform that isometry and I imagine myself being acted upon by that isometry. I can ask, well, now is what my counterclockwise, is that now clockwise or counterclockwise? If it's still counterclockwise, you preserve third orientation. If it's switched, you have reversed orientation. So there's this notion of orientation preserving isometry, and that's what I'm just defining. So if we have an orientation preserving isometry, let me just say what they are, and then we'll continue next time. So it's either a translation, TD, or a rotation about, which means, and that's surprising to me, should be surprising to you a little bit, because we know we have something that preserves our orientation. We just classified them as compositions of translations and rotations. What we're saying is that no, actually some person has some grid where it's actually whatever it is, it's just a rotation about that person. There's always a center to the isometry of its orientation preserving, or it's just gliding along. Okay, so we'll show that next time and keep on going. All right, thanks everyone.